Hi everyone, this is Mrs. G, and today we're going to learn about transformations of functions. So before we start, I have a quick warm-up for you guys, so please pause the video and give this a try, and we'll check your answers in just a few seconds. Okay, go ahead and check your work. This is just one possible answer that works, so a few things that are really important. You should have zeros at -4, 0, and 5 because those are the times when we're changing from positive to negative. And you should have a hill at when x equals -2 and a valley when x equals 3. Now the height of that hill or the depth of that valley can change as long as they occur at those points, because that's when you are changing from increasing or decreasing. So you could maybe have a graph that looks more like this. So maybe it's something around here, and then maybe this actually goes a lot farther, as long as it is changing again from increasing to decreasing at these x values, and it goes through these zeros, because that's when we're changing from positive to negative. So for this, there's actually really an infinite number of graphs that could work. That's why I just said sketch a graph that has the following characteristics. So today we're going to learn about different types of transformations and how we can apply them to any type of function. So there are 6 types of transformations we'll be working with. There are translations, which are shifts. There are stretches or shrinks, and there are reflections. And then for each of those, we have vertical and horizontal versions of each. So let's start with the translations. Again, translation is just a fancy word for a shift, meaning we're just simply shifting our graph up or down for vertical. So it might look something like this. If we're shifting our graph down, maybe something like this. So notice the shape of my graph is unchanged. It's a rigid movement. We're just shifting every point down 3 units. Or a horizontal translation or shift, we're just moving all of our points left or right by the same number of units. So it could look something like this. This would be a horizontal translation to the right 2 units. So again, it's a rigid movement. The shape, the orientation of our graph remain the same. We're just shifting everything left or right for horizontal. Now for stretches or shrinks, again, there's vertical and horizontal. So for these, you're essentially going to well, for vertical, you're essentially taking any y value and you're multiplying it by your stretch or shrink factor. So here we're just changing the y values of each coordinate. So let's say we're going to do a vertical stretch by a factor of 2. All of our y values are going to double. So this y value at 0 stays the same. This y value here is at 1. We're going to double it, and we're going to bring it to 2. This 0 times 2 is 0. And then this y value at -1, we'll double it to -2. So it looks something like this. So we're doubling all of our y values, or we're multiplying our y values, because it's vertical, by whatever our stretch or shrink factor is. Now for horizontal stretches or shrinks, we're going to be changing the x values of our coordinates. So for this, it's a little bit trickier because there is a reciprocal rule, which we'll talk about. But again, here our y values are going to remain unchanged. We're going to multiply all of the x values of our coordinates by the reciprocal of our stretch or shrink factor. So if we have a horizontal shrink, maybe by a factor of 1/2, again, all of our x values are going to be cut in half. So this x value will move to here. Well, this one will stay at 0, this one will be cut in half, this one will be cut in half to here, so something like this. So again, we're multiplying just our x values by that stretch or shrink factor instead of the y values. The last 2 are reflections. So there's a vertical reflection, which would be a reflection over the x-axis. It would look something like this. So essentially, all of our y values become opposite. We multiply all of our y values by -1 to reflect over the x-axis. There's also a horizontal reflection, which would reflect over the y-axis. Here, since it's horizontal, we're changing all of our x values. We would essentially multiply all of our x values by -1, and that will reflect us over the y-axis. So it would look something like this. So a general rule of thumb here, anything vertical is going to affect our y values, and anything horizontal will affect our x values. So here in this chart, we have some more general rules of transformation. So whenever you're trying to apply a transformation, first you're going to ask, what do you want to do, and then which direction do you want to do it? So what do you want to do? If you want to translate or shift your graph, you're going to add or subtract to either x or y. If you want to stretch or shrink, you're going to multiply by a positive number to either x or y. So stretches or shrinks, we multiply by a positive number. And if you would like to reflect your graph, we're going to multiply either x or y by -1. Now, once you know what you want to do, you have to decide what direction. If you want to do anything horizontally, again, you're going to apply it to the x. If you want to do something vertically, you don't want to apply it to the x, you want to apply it to the y. So we'll add this in, apply to y. We say group with x or don't group with x as it applies to what your equation looks like. But again, anything horizontal will affect x, anything vertical will affect your y. So this right here is a kind of general equation for all translation or transformations. So usually the parent function would look something like this. I'll say p of x for the parent function. It would just be x. So you see here, here's the x, but there's all these different changes. So let's go through it. First, within the parentheses, you see that we can add or subtract h from our x value. So since we're adding or subtracting, this is a translation. And since it's to the x, it's horizontal. One thing to note here, do you guys see this negative that's built in? This implies that any horizontal translation will actually move in the opposite direction that you think. So if you see x minus 2, it's actually going to move to the right 2, and if you see like x plus 2, it would actually move to the left 2. That negative is really built into the function. Now if you look out here, we see a plus k, so we're adding some value or subtracting, so that means that it's going to shift our graph, it's going to translate it, and since it's not grouped with the x, you can see it's outside, it's going to be a vertical translation, so it will affect your y values. Here then you see some multiplication. If you see multiplication on the outside, so it's not grouped with x, that's going to be vertical, and it's going to be a stretch or shrink. And if you see it multiplied on the inside, so you can see it's kind of grouped with where your x value is, it's going to be a horizontal stretch or shrink. And again, we'll talk about this more in a second, but it's actually going to be by the reciprocal of this value. And then the negatives are not added in, but if we had a negative on the outside, it would be a vertical reflection, so over the x-axis. And if we had a negative on the inside grouped with x, we would have a horizontal reflection over the y-axis. One thing I also want to point out is you'll see here this b value, this horizontal stretch or shrink, it always needs to be factored out from x if there's also a translation. So sometimes you won't have a translation, so you won't need those extra parentheses, but this b needs to be factored out from a translation. So down here we're going to talk about how we can change a function to apply a certain transformation. So these are going to be all of our vertical transformations. So you can see here's f of x, which again represents the y values. So if we add k to our function, it's going to translate up k units. If we subtract k from the entire function, it's going to translate our graph down by k units. If we multiply our y values, remember f of x is interchangeable with y. If we multiply our y values by a, it's going to be a vertical, again these are all vertical, stretch or shrink by a factor of a. And we'll talk about how to determine if it's a stretch or shrink in just a moment. And then if you see that we're multiplying all of our y values or our entire function by a negative, it's going to reflect vertically, so that's over the x-axis. Now let's look at the changes, the horizontal changes, if we want to change what our function looks like. Again, here you can see that we're specifically adding h to x. It's grouped with x. So this will actually translate or shift our graph to the left by a units. Remember, this always moves in the opposite direction. This will translate our graph to the right by h units. Here we're multiplying, so again this is going to be a stretch or a shrink. So this is again a stretch or a shrink, and this is the tricky part. For this one, it's by a factor of 1 over b. It's by a factor of 1 over b. So we do need to be careful. Whatever value you see in your equation, the stretch or shrink factor is actually the reciprocal, which will affect whether it is a stretch or a shrink. So we'll talk about that again in just one moment. And then here you can see that we have a negative multiplied to the x specifically, so you can kind of compare the differences here. If it's multiplied to x, it's that horizontal reflection, so it's going to reflect over the y-axis. Now let's really quick talk about that stretch or shrink. We call something a stretch if the factor, the stretch factor, is greater than 1. So if it's by a factor of 2, we would call it a stretch. If it's by a factor of 3, we would call it a stretch. And then we call it a shrink if the factor is between 0 and 1, so A or B. So again, if it's A, or we would say if 1 over B is greater than 1, and here 0 is less than 1 over B is less than 1. So again, we always take the reciprocal of whatever we see here. If that factor is greater than 1, we would call it a stretch. If that factor is between 0 and 1, we would call it a shrink. And again, between 0 and 1, because this stretch or shrink should always be positive. The negative, I want you to think of that as a separate transformation. That's a reflection. Okay, so we're going to try some of these together. We're going to be rewriting a new function, which we'll call g of x, in terms of f of x according to the following transformations, and then we're going to do our best to sketch a graph. So let's say that this is f of x, and we want to translate it up 4 units and left 2. So our new function, g of x, we're going to take our original function, which was f of x, to shift it left 2, we would add 2 to x, so it'd be f of x plus 2. And then to shift it up 4, we would add 4 to our entire function. So this, since it's horizontal, needs to be grouped with x, and remember it's always opposite. This, since it's vertical, should not be grouped with x, and since it's up, we add. So that one is not opposite. Now to apply this change to our graph, we can take some clear points that we see. So maybe I'll take this point, this point, this point, this point, this point, and we can simply shift them up 4 and left 2. So up 4, left 2, up 4, left 2. So take points that are clear and easy to move. Up 4, left 2, up 4, left 2, and up 4, left 2. And it would look like this. So you can see that the shape and the orientation of our graph are unchanged. They're both rigid movements. We're just simply translating or shifting them. Okay, let's try this next one. So f of x is stretched vertically by a factor of 2 and reflected over the x-axis. So these are both vertical changes. So we're going to be applying them to f of x, not to the x specifically. So our new function, g of x, we're going to take the original function. Since it's a vertical stretch by 2, we're going to multiply our function by 2. And since it's a vertical reflection over the x-axis, we multiply the outside by negative. So we can do the same thing to our coordinates to help us graph our new one. So again, this should only affect our y values because both are vertical. So we're actually going to multiply all of our y values by -2 to help us graph. So this point, we multiply the y value by -2, it would become here. Our next point goes here, 0 stays at 0. This point would go here, and this point would go here. So you can see that this reflects, and it's a vertical stretch. So again, anything vertical should only affect the y values of our coordinates. Let's look at this next one. F of x is horizontally shrunk by a factor of 1/2. So this is a tricky one. So our new function g of x. So since it's horizontal, we're going to be multiplying our x. Specifically, we're going to group it with the x. And it is shrunk by a factor of 2, but when we write it, we're going to write the reciprocal of that. So since the factor is 1/2, the b value is actually going to be 2. So it's going to be 2x. So it is still a shrink because the factor is 1/2, but what you see in the equation would be a b value of 2, the reciprocal, again, of the shrink factor. So that means that we're actually going to take all of our x values, so we'll take those same coordinates that are nice and easy to work with. All of the x values, we're going to multiply them by 1/2, not by 2. We're going to multiply all of our x values by 1/2. So this point would move here, this point would move here, 0 stays the same, this point moves here, and this point moves here. So again, we're multiplying the x values by 1/2. So you can see this is a horizontal shrink. Imagine you put your hands on either side of your graph and you move them together. It would compress your graph in this way. Okay, this last one, f of x is reflected over the y-axis, which is a horizontal reflection, and vertically shrunk by a factor of 1/2. So our new function, g of x, we have a vertical shrink, so we're going to multiply the entire function by 1/2. Vertical is not grouped with x, but we have that horizontal reflection that is grouped with x, so the negative gets multiplied to x. So for this one, all of our y values are going to be multiplied by 1/2, and then all of our x values are going to be multiplied by -1. So there's two changes here. So here's the points we'll be working with. So again, our y values are multiplied by 1/2. So this would be half the distance, and then we multiply our x values by -1. So it would actually reflect it over here. This one, you go half the height, and then you reflect it. 0 stays the same. For this one, the y value is cut in half, and then you multiply the x value by -1. And here, the y value is cut in half, and you multiply the x value by -1. So you can see that our graph kind of looks like if you put your hands on the top and bottom and squish it down, that's a vertical shrink. And you can see that it is reflected over the y-axis. All right, so at this point, please pause the video and give these a try on your own, and we will check your answers in just a few seconds. All right, go ahead and check your work here. So if you want to translate left 1, you should add 1 to x. Down 5, you subtract 5 from your entire function. And these are the 3 points that I thought were easiest to translate accordingly. So I just moved each one left 1 and down 5. For this next one, the reflection over the x-axis is vertical, so we multiply the entire function by negative, and it is a horizontal shrink by a factor of 1/3. In the function, our b value is the reciprocal of that, so we write a 3 here, but we're still shrinking all of our x values by 1/3. So you take any x value and you multiply it by 1/3, and then you reflect any coordinate over the x-axis. So anything that's on the x-axis, it stays in the same spot. And this last one, a vertical shrink, you multiply your entire function by 1/4, and then to reflect over the y-axis, you multiply x by -1, because that is a horizontal reflection. This actually doesn't affect our graph because it's symmetrical about the y-axis, but the vertical shrink does affect our graph, so you can see that instead of being at 0,4, I'm at 0,1. All right, so now we're going to practice looking at equations of functions and describing in words the transformations we see. So first, we're going to describe the transformations seen in f of x in reference to the parent function p of x. So this first one, our parent function is simply x squared, the most basic quadratic. And then here you can see we have f of x. So I see three transformations. We have a negative, we have a 2, and we have a 7. So none of these transformations are specifically grouped with the x, which means actually all of them are vertical. So let's start with this one. This is a vertical reflection, which is a reflection over the x-axis. So that's the negative. The next thing I see is we're multiplying the entire function by 2. So that's going to be vertical. Again, it's not specifically grouped with x. I know it's right next to it, but you would specifically see it in parentheses if it were. So this is going to be a vertical stretch by a factor of 2. Again, vertical stretches, the factor matches the number you see. And then this one, again, it is not specifically grouped with your x value, so it's still vertical. This is going to be a vertical translation because I'm adding, and it's going to go up 7 units. Okay, if you look at this next one, our parent function is square root of x, so it's the radical function. Here's new f of x, so I see a few different transformations again. So let's start with this one on the outside. This one, we're multiplying on the outside of our function. So this would be a vertical. This one is a shrink because the factor is less than 1, so by a factor of 3/4. The next thing we can see here is there's a negative, and it's grouped with where x is. See how it's within the radical? That means that it's grouped with x. So that's a horizontal reflection, so that will actually reflect over the y-axis. The next thing I see is that we are adding 5 to x, so it's specifically grouped with x, so that means it's horizontal. This is a translation because we're adding. Remember, it moves in the opposite direction for x, so this is actually going to go left 5 units. And the last thing I see is outside of our radical. It's not grouped with x, and so that means it's going to be vertical. So this is a vertical. It's a translation because we're subtracting, and it's going to go down 2. Next, you'll see our parent function is the sine of x, and our new function f of x. So we have a couple different transformations here. Now this one, there is a trick to this. As I mentioned briefly, anytime we have something like this where we have a horizontal stretch or shrink and a translation, we need to make sure that this is factored out from the rest of the binomial. So we actually have a step we have to do first. We have to factor the 3 out, so it's actually 3 times x minus 2. This is tricky, and it's something you have to know to do. If you don't, you're going to think that this graph shifts to the right 6, but it's actually only shifting to the right 2. So you do need to make sure that any stretch or shrink that is horizontal is factored out from the translation. So now let's assess what's going on here. Let's start by talking about the 3. So again, this will be horizontal because it's grouped with x. It is going to be a stretch or shrink because it's multiplication. Now remember, the factor is the reciprocal. So the reciprocal of 3 is 1/3. Since it's 1/3, we're actually going to call this a shrink because it's less than 1. So by a factor of 1/3. So that is a little tricky. The next thing we can see is this x minus 2. So again, it's grouped with x, so it's a horizontal. It's a translation because I'm subtracting, and again, this moves in the opposite direction by right 2. And then the last thing we see is that plus 1 on the outside. So since it's not grouped with x, it is vertical. It's a translation because we're adding, and it's just going to go up 1. So there you go. So again, watch out for something like this. We do have to do that step first of factoring out the stretch or shrink. All right, I have a couple for you to try, so please pause the video and give these a try on your own. We can check your answers in just a few seconds. All right, go ahead and check your work here. For part A, there was that extra kind of tricky step of factoring out the 2 before you assess the transformation. So this is a horizontal shrink by a factor of 1/2. This is actually a shift to the left 4, so don't forget to factor out the 2. And this is a vertical translation up 5. Here we have 4 transformations: a reflection over the x-axis, vertical stretch by 3, horizontal translation right 3, and a vertical translation down 1. Now we're going to be using our transformations to help us graph. So we can do this for any type of function, and the rules are the same, again, for any type of function. So first, you can find coordinates from the parent function of your graph, and then apply the rules of transformations to the individual coordinates. So we're going to add, subtract, multiply, maybe multiply by a negative, depending on what you're trying to do. And here's our big tip for today. Always follow PEMDAS when you are applying transformations. PEMDAS is order of operations, right? We should always apply transformations that require multiplication before we add or subtract. So just keep that in mind when we apply transformations. We do it kind of in the same order that we follow for order of operations. Okay, let's give one of these a try together. So here we have a quadratic function with a whole lot of transformations. So that might be a little bit daunting to graph. So let's start by finding some coordinates from our parent function, which would just be x squared. So again, it's just the most basic form without any transformations. So let's find some points from this. So we could do -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. If you'd like, you can sketch a graph of your parent function just to see what it looks like. So it looks something like this. I'll do it with a dotted line. You don't have to do this, but you can. And now we're going to look at the transformations and see how it will affect our x and y values. So let's start with the horizontal transformations. I see 2. Here I see a horizontal stretch by a factor of 2. So again, it's always the reciprocal here. So I'm actually going to multiply all of our x values by 2. And then here, this is going to shift our graph to the left 1. So we want to subtract 1 from all of our x values. And then for our y values, there's 2 vertical transformations. It's going to reflect our graph vertically over the x-axis. So I multiply all my y values by -1. And then I'm going to shift down 5, so I'm going to subtract 5 from all my y values. So that we can apply these changes to all of our x and y values. So let's do that really quick. Okay, so you can see that I've applied those changes, and these are my new coordinates. So then I can just plot these coordinates, so -5, -9, -3, -6, -1, -5, 1, -6, and 3, -9. And you can see that we do have that horizontal stretch by a factor of 2. So our graph is wider. It's been reflected vertically, and then it's been shifted to the left and down. So you can see that all of our transformations are correct. All right, so please pause the video and see if you can kind of use that same process to help you graph this graph. So here, this is an x cubed parent function graph. So start with those parent function coordinates. You'll have to find new ones, should be different than the previous example, and then apply the changes. All right, go ahead and check here. So these are the coordinates I used for my parent function, and it looks something like this. So this is our cubic function. I scaled my y-axis by 2, just so you know. And then I applied the changes. So this shifts our graph to the right 3, so we add 3 to all of our x values. We have a vertical stretch by 2, so we multiply our y values by 2, and then to shift our graph up 2, we add 2. So this gives us the new coordinates from our graph, which you can plot right here. You'll see that our graph is kind of stretched out vertically. So you can see it's not quite as flat, and it has been shifted to the right and up. The last thing we're going to talk about today is a way we can classify some functions. So some functions we can classify as either even or odd. It's very possible that it doesn't fit either characteristic, so we could say neither as well. So an even function is, by definition, a function where g of negative x is equal to g of x. Meaning if you plug in the same positive and negative x values, it gives you the same y value. So here, let's say I plug in positive 1 and it gives me positive 1, and I plug in negative 1, it gives me the same y value of positive 1. So all even functions are actually symmetric over the y-axis. And then by definition, an odd function is when h of negative x equals negative h of x. So what does that mean? It means if I plug in the opposite for x value, I actually end up with the opposite of the y value. So here, let's say I plug in positive 1 and I get positive 1. If I plug in the negative version of that, so let's say I plug in negative 1, I should get the negative y version. And this one is actually symmetric about the origin. So it's a rotational symmetry, so it's reflected about the origin rotationally. So we're going to check algebraically to see if these functions can be classified as even or odd, or we would classify them as neither if it doesn't fit. So to do this, we check to see what happens when we plug in f of negative x. So we're going to plug in f of negative x, and then we're going to simplify it to see what happens. So we have negative x in parentheses squared minus negative x cubed. So when we have f of negative x, if you square a negative, it becomes positive. So we have x squared. Now, if you cube a negative, it stays negative. And then we multiply this by another negative, so this actually becomes positive x cubed. So let's compare our original function to what we have here. So by definition, if f of negative x gives you f of x, it would be even. This is to see if it is even. So when we plug in f of negative x, it is not the same as our original function. So we would say, okay, this is not even. And then by definition, for odd, again, if we plug in the negative, it should give you the exact opposite of the entire function. So you'll see here that this part is the same and only this part is opposite. So we could also say that this one does not meet the qualification for odd. So again, if the entire thing was opposite, maybe if this changed to negative and this changed to positive, we would call that odd. But this does not meet the requirement for either even or odd, so we would call this neither. Okay, go ahead and pause the video and apply the same test to see if you can determine if this function is even, odd, or neither. Okay, so go ahead and check your answer here. If you substitute negative x for all of your x values, and then you simplify, you actually end up with the original function, because if you raise any negative to an even degree, it becomes positive. So since f of negative x is equal to f of x, we say that this function is even. All right, that is all for today's lesson. Thank you so much for watching.